All right. So welcome to lecture two of the course. So last week we had like an introductory session into statistics, the definitions that we needed to know, and all of that. So now we'll move on and talk about some technical details, right? So this is still a gentle introduction into statistics for now. So we're going to start talking about descriptive statistics, the first branch that we usually cleave statistics into two branches. We talk about descriptive statistics and inferential statistics, and for this week and the next week we'll talk basically about descriptive statistics. All right. So what the plan of action here is to talk about five key ideas. All right. So the first thing is to first two sets are to basically do preliminary data visualization to just get a visual sense of what the data set looks like and what the key features of the data set look like. All right. Then we'll talk about getting a few summary statistics out of that data set to again give us now a more analytical description of what's happening, right? So you can think of this as the first two sections of this is about getting a visual description of the data set, and the last three sections of this chapter will talk about getting basic analytical descriptions of the data set, so-called what we call summary statistics, right? So let's get into it. So let's talk about frequency. Let's begin with frequency distributions and their graphs. Okay. So before we talk about a frequency distribution and all the other things which go along with it, there's some key ideas about limits, midpoints, relative frequencies, cumulative frequencies, boundaries, and then how do we construct what we call frequency histograms, frequency polygons, relative frequency histograms, and ODIs, right? So that's all the things that we'll have to do to understand basically a frequency distribution. But let's start with a basic understanding. Okay. So let me start with an example and I'll come back to this. Okay. So here's a typical situation, right? I send you out I want to know what the GPS, I'm in the market to buy a GPS and I want to know, okay, can I know what different price points do these GPS devices sell at, right? There's a wide range of price points. So I send you out to go collect some data, right? That's how I figured this out. So I send you out and say, okay, why don't you visit a bunch of stores, go up to their GPS, all the GPSs they're selling, and look at the prices and record what the prices are, and you come back and you give me this list. Okay. Now, if I look at this list, there is prices as low as 90 bucks, 70 bucks, $59, and I can buy something for as high as 450, and I can straight away begin to see that there is some I can start to make sense of what I'm looking at. What's the range of values I can be looking at? Okay, but this raw numbers don't convey much meaning, right? It's just you've given me 30 odd numbers and they're not recorded in any particular order. There's no rhyme or reason to the way it's been recorded. It's just recorded the way you saw them, and that's basically what we have here. Okay. The point of descriptive statistics is to take this kind of unsorted data which is just raw, what we call raw data, and begin to impose a measure of order onto it, like some way of sorting through this data and then thinking through the issues here. Okay. So when we talk about sorting through this data, the primary way we can sort data is through what we call a frequency distribution. Okay. So what do we mean by frequency distribution? Okay. So here's this data here, 30 data points. The first thing for me is that think of this as a sorting metaphor, right? Like I have a bunch of unsorted things. What do I, what is one primary thing that you can think of as a way of sorting these things? You can just get some bins, right? You can label each bin and like items belong in each bin. And now you can sort them into a number of different bins, okay? So number of bins that we sort them into are what we call classes, right? We can divide up the entire data set and sort the data set into classes. Now I've arbitrarily chosen to divide it up into 7 classes. Generally speaking, this is, as a statistician, you can make a judgment call of how large a class size should be. But for the sake of the argument, let's say I want to divide up this entire data set into 7 different classes. Okay. So number of classes I want the data set to be sorted into is 7. Okay. The second question becomes, how large should each of these classes be? How large should each of these bins or boxes that I'm going to sort the data into, how large should each class be? And the logical thing is to say, okay, let me see how wide the data set is, and then divide it up into 7 equal parts. So that's the first part of this. This is the max minus min tells me, right, how large the data set is. Where is the starting point, which is 59 here in this case. So my data set starts at 59 and ends at 450, right? So it tells me that the data's max value is 450, the data set's max value is 450, the min value is 59, the minimum value is 59. So that tells me how wide this data set is. This is also what we call the range of the data set. The max minus the min tells us the range of the data set, how large that range is going to be. Okay. So given that I know that this is the distance between the max and the min value, given that this is the range of the data set, and I know I want to sort them into 7 classes, I can divide the range by the number of classes and get basically this width of each of these classes, right? 7 equal parts. 1, 2, let's say 3, 4, 5, and then 6. Okay, okay. I mean, obviously I can't draw it perfectly, but you can imagine that these are equal parts. So given that I know the size of the data set, the range of the data set, now I can divide that up and figure out how large each class should be, which is what we call class width. The class width essentially is telling me how wide each of these categories into which I'm going to sort the data into should be. All right. So in this case, if I take 450 minus 59 over 7, that's 391 over 7, that's 55.86, and I can just round it up, right? I can round it up to 56. So it's because if it's greater than 0.5, 55.5, then I'll round up to 56. If it's less than 55, then 0.5, then I'll round it down to 55, okay? So that tells me the size, okay? Now, given that, I need to be able to label these boxes. And how am I going to label these bins? I'm going to label these bins with their minimum value that the box will contain and the max value that the box will contain. So this is how we calculate these lower limits and upper limits, right? The first box will start at 59. And where will it end? It will end where the second box begins, and the second box begins where it's 59, plus I have to travel the size of the class width, which is 56. So if I add 56 to 59, that tells me what the lower limit of the second class is going to be, which is 115, right? And then I keep doing this entire enterprise. So like 115 plus 56 is going to be 171, right? So if I look at where the third class begins, then it should be 115 plus the class width, which is 56, so 171. The fourth class will begin at 227, which is basically 171 plus 56. 227 plus 56 is 283. 283 plus 56 is 339. 339 plus 56 is 395, right? So now I found where the uh, upper limits of each of these classes are going to, lower limits of each of these classes are going to. Okay. Now I know that all these numbers are basically whole numbers. There's no decimals, there's no fractions, there's no point something. So what I want to do is to make sure that I have mutually exclusive classes, which is to say, I don't, if I imagine the number 115, right? I don't want 115 to be both in the first class and the second class, because I wouldn't know where to sort it into. If I pick up a number like 115, does it belong in the first class or the second class, right? So in order to avoid that confusion, what I can do is that in the first class at just before the second class begins, right? So if the second class begins at 115, if the lower limit of the second class is at 115, then the first class needs to end just before that. So I close it off at 114. And this tells me that my first bin, the first box or the first class that I'm going to have is going to contain in all the GPS numbers, which are between 59, which is the lower limit, and 114. The second class will contain all those GPS prices which start at 115 and end at 170. Where do I get this 170 from? If the third class is starting at 171, then the second class needs to end just before the third class begins. So it's going to end at 170. Okay. All right. So this is how I can basically construct a series of classes, right? So the first class is going to be 59 to 114. The second class is 115 to 170. The third class is 171 to 226, and so on and so forth. So one thing to really make sure that you understand is that the class width, it's natural to think that the class width is wherever the lower limit, the upper limit minus the lower limit should be the class width, but that's not necessarily true, because what we are doing is that the lower limits are telling me where the next each class begins. So the class width itself, so even though there's a gap between 114 and 115, that gap you need to account for. So if I take the difference of any two lower limits, any two consecutive lower limits, or any two consecutive upper limits, that should always be equal to the class width. And that's true everywhere. Look, if I take the difference between these two upper limits, 450 minus 394, that's 56, right? And if I take the difference between any two consecutive upper limits or any two consecutive lower limits, that pattern is going to hold, that the difference there is always going to be equal to 56. All right. And this is how I basically get my lower limits and upper limits. So think of it this way, like the metaphor is very useful to think of this as analogous to, I have a pile of unsorted things. So first I get a bunch of bins to sort them into, right? Now the question is, how many bins do I need? Now, as a statistician, you can make that choice, right? You make the right number of bins. You can approximate what kind of bins. In this case, I said I want 7 bins, or I bought 7 bins, let's say. Okay, so I have 7 classes I want to divide them into. So now I have 7 bins. It doesn't make sense to just throw entries into each of these bins without first labeling them. Okay, so the labeling mechanism is in order to label these boxes, one way I can label these boxes is to basically make sure that I can label them as to what they contain, right? And so I have now a labeling scheme. How do I label this labeling scheme? The first box will start at the minimum value in the data set, which is 59. The second box will start at 115, which is wherever the first box began, plus the class width, which is 56. So the second box will start at 115. The third box will start at 171, and so on and so forth, right? I want to make sure that each of these boxes contains, if I don't want any entry to belong to two classes at the same time. Either it belongs to one class or the other. What I want to create are mutually exclusive classes. So in that sense, if the second class is going to begin at 115, I want to close off the first class just before that, just prior to that. So let's say I close it off at 114. And now I have upper limits and lower limits. So I have my 7 bins. Each of them has their labels, and they label with this lower limit, upper limit. Okay. Now the question is, okay, now I have my bins, I have my classes. Now I need to make sure that I can uh, start sorting the data into these bins, right? So how do I go about that? So, okay. So I pick up a number like 90, right? If I think about a number like 90, it belongs in the first class because the first class will contain all numbers from 59 to 114. So that's where I get a tally mark here from, right? So I'm essentially trying to figure out how many entries are going to be in each class. So if you look through that raw data set, there's 4 entries which are between 59 to 100, 5 entries which are 1, 2, 3, 4. Oh, there should be a tally like this. So there's 5 entries which are in between 59 and 114. So this is what we call the frequency. The frequency tells me the number of entries which are in each of these boxes. Okay, so it tells me that there is 5 entries in my data set which are between 59 and 114, and I can continue this process. I can do this counting. Just to make this easy, you can do these tally marks. So every time you find an entry which belongs in a class, you just put these vertical lines, and after you have 4, then you cross them out. So together this unit here is read as 5 plus 3, which is 8, right? So frequency here is 8. And for the third class, which is between 171 and 226, there's 6 different entries. And how am I getting these numbers? I'm just looking at my raw data set, right? And making these tallies. So 90 belongs in the first class, 130 belongs in the second class, 400 belongs in the last class. And I keep going through that process, making these tallies and then counting them all up, right? So the frequency, what we call the frequency, is just giving me a count of how this data is distributed, right? It is giving me how many entries are in each of these different classes that I've constructed. And straight away, instead of looking at just a pile of 30 odd numbers on a piece of paper, I have a better way of imagining and visualizing and seeing this information, because now it's more meaningful. It gives, straight away I can see that, oh, there's a lot of GPSs which are priced between 59 and 282, for instance, and not as many. There's not a big market for very expensive devices, right? And so straight away, I'm beginning to understand some patterns in the data set, and I'm beginning to describe what it is that I'm seeing inside the data set in a nice, coherent fashion, right? Instead of just a pile of numbers, now I have like a clean table, which gives me more meaningful information. Okay, and that's basically the goal of descriptive statistics, is to take some raw data set and begin to impose some structure, some cohesive structure on top of that data set to extract some meaningful insights and information about it. Okay. All right. So another thing that I might want to do here is to basically have a labeling mechanism where we might use the midpoints as the labeling mechanism. Okay. And midpoint is fairly straightforward. It's the midpoint of a class. So you take the lower class limit, add the upper class limit to it, divide by 2. That tells you where the midpoint is, right? So this is how we find the midpoint in between any 2 points, and that's straightforward enough, right? So if for the midpoint of the first class is the midpoint between 59 and 114. So 59 plus 114 over 2, that's 86.5. That tells me the midpoint of the first class. Similarly for the second, the third, and so on and so forth. So I can get all these midpoints together, all right? So why we might want to calculate the midpoints, I'll get into it in a second. But it's important to know that, yeah, okay, so midpoint is basically the midpoint between the class limits. So the upper class plus the lower class divided by 2, the class limits, that's what tells me the midpoint. Okay. Another useful idea here is to think about the relative frequency. The relative frequency tells me what portion or what proportion of entries are in each class, what percentage of entries, or what fraction of the entries of the data falls into a particular class, right? So how do I calculate it? I basically look at the size of the sample size. This tells me how many total entries there are. The frequency tells me how many entries there are in a particular class. So this is the fraction of the entries of the overall entries which are inside this particular class. So the relative frequency is given by that. So here you can see straight away that in the class between 59 to 114, of the 30 entries, total entries that I have, 5 of them are in the first class. So the fraction or proportion of the data which falls into the first class is 5 over 30, or 0.17, right? So you can read this as a percentage as well. So if I multiply this by 100%, that tells me that about 17% of data is between this range 59 to 114. So 17% of the GPS prices that I've collected are between 59 and 114. Similarly, for the second class, if you think about the relative frequency of the second class, of the 30 total entries I have, 8 of them are in the second class, right? So 8 over 30 is 0.27, or about 27% of the data set is inside the second class, and so on and so forth. So I can always calculate relative frequencies. And this tells me again a bit more useful information. So the frequency is just telling me what the count is in each class. The relative frequency is telling me what is the proportion of the total data which lies inside each particular class, and straight away I'm getting more and more information. So instead of just staring at a piece of paper with 30 numbers on it, now I have more useful insights into the data set. And that's what we're trying to do with descriptive statistics, is to basically get somewhat more useful insights into the data set. All right. The other thing that we might want to calculate is what we call the cumulative frequency. The cumulative frequency, as the name suggests, is essentially telling me at the end of each class, how much of the data have I already seen, right? That's what it tells me. It tells me the sum of the frequency for that class and all the previous classes that have come before. It just is giving me a description of how much of the data is already been seen, right? So if I think about the cumulative frequency of the first class, at the end of the first class, by the time I hit the entry 114, I've seen 5 entries, so the cumulative frequency is also 5. Okay, so I've seen 5 total entries so far. By the time I hit the second end of the second class, by the time I hit 170, I've seen 5 entries in the first class, and but I've also seen 8 entries in the second class. So together, 5 plus 8, this tells me that I've seen 13 total entries. So it is telling me the cumulative accumulated count of the number of entries I've seen by the time I've hit the end of each particular class, right? So it's giving me straight away a description of the distribution of the data itself, right? It's telling me how the data set, where the bulk of the data set is, and where the tail of the data set is. It's going to give me a description of how the data set itself is evolving as I go down these classes, right? So by the time I hit the entry 226, the cumulative frequency is all the entries I would have seen by the time I hit 226, which is the 5 entries in the first class, plus the 8 entries I would have seen in the second class. So that's 13 entries, plus the 6 additional entries in the third class, which tells me that I've seen 19 total entries. Okay. So bringing all of this together, we have a nice little descriptive table, right? This is what we call a frequency distribution table. So here we have first all the classes that we are going to use, all the labels. So first we decided that there are going to be 7 bins. Then we said, okay, how do I label each of these bins? So we came up with this naming mechanism where we found the class width and figured out what the limits of each of these bins should be. So we put the label on it. Then we took these entries and sorted them into these 7 different bins. And now you're giving me all the information from it. You're telling me that in the first bin, if I think about what this row of information is telling me, the row of information tells me that the first bin into which the data has been sorted is between 59 and 114. The frequency is telling me how many entries are inside that bin. The midpoint, we'll get into it in a second why it's useful, but it's telling me the middle point of that class, so 59 plus 114 over 2. The relative frequency is telling me what fraction of the data is in this class. So of the 30 data points, 5 over 30 or 0.17 or 17% of the data set is in the first class. And the cumulative frequency is telling me by the time I finished looking at this class, how many entries I've already seen. In this case, it's 5. And so this is how it goes. Okay. There's a couple of things to note here. If I sum the column of the frequency, right? If I take the sum, so here this is the Greek symbol for this is what we call sigma. Sigma is the Greek notation that we use in mathematics to represent sum. So this says that if I sum all the frequencies together, so which is to say, if I add these column of numbers together, what should they add to? They should add to the total size of the data set, right? Because all the entries are either in one box or the other. And if I add up the total number of entries in all the boxes together, that should basically tell me the size of the data set, in which case it should be equal to 30. Okay. Similarly, if I take the sum of this relative frequency column, right? This is sigma again here is sum of f over n here is f over n as a relative frequency. So the sum of the relative frequency column should always be equal to 1, which makes sense because if 17% of the data is in the first column and 27% of the data is in the second column, and if I add all of these numbers together, 100% of the data is going to be in one of these boxes, right? Let's make sure that all the data points that I have been sorted into one box or the other. So if I add the relative frequencies together, that should always sum to 1. Okay. So this, you can read this also 100%. So if I read these as percentages, so if I multiply that by 100%, that's 100% of the data is in one of the 7 boxes I've chosen. Okay. So here we started with 30 raw numbers on a piece of paper, and you can see it becomes much more useful when you're dealing with extraordinarily big data sets, right? If the data set is, hundreds and thousands and tens of thousands, or millions of entries even, this gives us a nice clean one table view, a snapshot. It's not giving us all the detail, but it's giving us a basic overview of what that data set looks like, what the basic description of that data set is. Okay. All right. So given that we have this table, we can actually make some graphs to visually see what is happening, and that's what we'll do next. Okay. All right. So let's look at the graphs that you can do. Okay. So let's think about graphs of frequency distributions. So for the first frequency graph that we'll talk about is what we call the frequency histogram. The frequency histogram is just going to chart out what the frequency of each of these classes is going to look like, right? One crucial thing here is that consecutive bars must touch each other, right? So the height of each of these bars represents the frequency of that class, and then consecutive bars must touch, okay? Now, if I look at how I've constructed this class, there is a gap here, right? Here there is 59, this is 59 to 114, and the next class is starting at 115, which means that there is a class, there is between the limits of the upper limit of one class and the lower limit of the subsequent class, there is a gap which is emerging. And in a frequency histogram, I can't have these gaps, because consecutive bars must touch. So in order to make sure these consecutive bars should touch, I come up with this notion of what we call class boundaries. So if I look at the first class, it ends at 114, the second class begins at 115, and if these two bars need to touch, the difference is 1. And basically, as with anything, I split that difference, right? So instead of closing the first class at 114, I close it at 114.5. And instead of opening the second class at 115, I will open it at 114.5, right? So now I have basically a way of making sure that consecutive classes are going to touch by constructing what we call these class boundaries, right? And similarly, that's what I do, right? The second class ends at 170 and the third class begins at 171. I want these two to touch, which means that I move this up to 170.5, and then I move the lower limit of the subsequent class down by 0.5. So this will begin at 170.5 and everything else stays the same, okay? Two crucial things to remember here is that in order to make sure that the class widths between any two subsequent limits, lower limits, upper limits, stays the same as 56, I need to adjust the class boundaries of the first class and the class boundary of the last class. So it won't start at the minimum value, it'll start slightly below the minimum value. So now this is adjusted down to 58.5, because if I take this difference between two subsequent lower limits, now this is still 56, and so is this, right? So in order to make sure that that stays consistent, we adjust the limits, the lower limit of the first class and the upper limit of the last class as well, okay? So we don't close it off at the min and max values. Now we instead adjust it so that those class limits stay consistently the same between lower limits, upper limits of subsequent classes, okay? Now that I have these class boundaries, I can now put down a frequency histogram. I know the frequencies, those are not changing. And now I can use this to basically graph this out, okay? I'll show you two methodologies of graphing this. So here's one, right? So the first class is starting at 58.5. The first class boundary, the lower class boundary is at 58.5, right? So this is where the labeling is coming from, 58.5. It ends at 114.5. So I know that this is 58.5 to 114.5. And the height of the first bar represents the frequency of the first class, which is 5. Okay, so this is how I get this first rectangle here, okay? The second rectangle starts at 114.5, ends at 170.5, and the height of that rectangle is given by the frequency of that class, which is 8. And now I have these series of rectangles, and this is what I call a frequency histogram. The third class begins at 170.5, ends at 226.5, and has a height of 6. The fourth class is here, height of 5, and so on and so forth. Okay. So this is one labeling mechanism where I'm labeling this graph with class boundaries. Okay. Now in most statistical software that you've seen, generally speaking, when we want to graph these things, we need only one value for the x-axis and one value for the y-axis. So in order to accommodate that, sometimes we might label them with class midpoints. So the midpoint here represents is the stand-in number for the entirety of that class. So instead of using two boundaries in order to represent the class, we're using a single point, which is the midpoint of that class, to represent the entirety of this class. So 86.5 is the midpoint of the first class, and then the height of that first class is 5. So sometimes you might see graphs which are labeled with class midpoints in order to make it easy to label and read, and sometimes you might see a graph with which is labeled with class boundaries. Whether it how it's labeled is a matter of convenience and what you're trying to achieve and what you would like to be readable in the graph, but it doesn't fundamentally change anything about the graph, right? Because the shape of the graph is still the same. The height of each bar still represents the frequency, and everything else goes through. So with the frequency histogram, remember that we are going to graph the frequency against either class midpoints, as it's in this case, or the frequency of each class against the class boundaries, as it is in this case. All right? Okay. So that's the first graph that you need to be familiar with: how to read, how to make a frequency histogram, how to read a frequency histogram, and so on. Okay. All right. A second kind of graph that you might often see encounter in statistics is what we call a frequency polygon, right? Frequency polygon is basically a very similar idea. It takes each class and then looks at how the frequency of the data set is evolving over time, right? So now let's look at this frequency distribution that we have here. So we have the midpoints and we have the frequencies, and we can just put these points down on a graph. So 86.5 is on the x-axis. When the midpoint is 86.5, this y-axis is just measuring the frequency, and so that's going to give me 5. So it doesn't have these bars representation, it's just a point representation. So essentially I'm putting down a pair of coordinates on a graph, right? So on the x value, it will be 86.5 as it is here. And on the y value, the corresponding y value will be 5. So that's how I get this point here. This is 8, when it's 86.5, the height should be 5. When in the midpoint is 142.5, the height should be 8. When the midpoint is 198.5, the height should be 6, and so on. Okay, that's how I'm going to get all of these points. Okay, now there's two special points here, one here and one here. Okay, if you look at these are not anywhere in the data set, right? They're not anywhere inside the data set. The point is that a polygon from geometry is a closed figure, which means that if I start from 86.5 and I stop at 422.5, which is where my data set is ending, what do I get? I get an open figure, right? It's not closed. Now, how do I turn this into a closed figure? I need to make sure that the endpoints of each side touch the axis. And the question is, where do I drop it down to, right? And the standard way of taking care of this is to say, okay, if the midpoint of the first class is 86.5, let's think of an imaginary class which has 0 frequency, which is to say there's no entries in this class, but it's at 30.5, and as the number suggests, it's 86.5 minus 56, which is the class width, right? And that's where I drop this down on the left-hand side. Just to close this figure out, there is no particular other reason to do this way than that. Okay, and the same thing here. The last class ends at 422.5, so I think of an imaginary class which is at 478.5, which has a 0 frequency, and now the figure has become closed, and I have a polygon, right? So this is what we call a frequency polygon. Okay, so that's one important thing to note as to where do we want to drop the endpoints of that polygon down into the axis, and by convention we just subtract the class width from the first midpoint to get this imaginary class with zero frequency on the left hand point, and then we add the class width to the last class to get this imaginary class at the end with zero frequency. And now we close the figure off and we have a frequency polygon. So instead of having these bars, which is what we use in a histogram, this is a polygon where we are not using the bars, but we're representing the frequency as a single point on this graph, and then we're adding them all, joining them all up. And now this gives us a nice little way of looking at how the frequency itself is evolving, right? We can see that the frequency is really high in here, right? You can see that the frequency of the GPS increases up to 142.5 and then slowly decreases from there. So there's a lot of increase in frequency here. Then slowly the count is beginning to come down. Okay. So that's the story with the frequency polygon, right? So sometimes you would see a frequency polygon, sometimes you see a frequency histogram. They're all conveying basically the same information. The point is that what are you emphasizing more? What is the emphasis more on? With the frequency polygon, you're emphasizing the evolution of the frequency rather than just the sheer, frequency, showing the frequency as a heights and in bars. So depending on what information you're trying to convey, you might choose one graph over the other, which is better suited to that particular thing. Okay. All right. Another graph that you need to be familiar with in statistics is what we call the relative frequency histogram. And basically it's the same as the frequency histogram. Instead of using the frequency column to chart, we are going to use the relative frequency column, right? So this tells me how the relative frequency itself is distributed. So I can take the class boundaries or the class midpoints. I can use either of these as the x-axis, and then on the y-axis, I use the relative frequency number. So the height of each of these bars is going to be equal to the relative frequency of that class, right? So here I have one of those. Again, these are labeled with class boundaries. So the first class is boundaries are between 58.5 and 114.5, and the height of this first class is now 0.17. So because it is a relative frequency histogram, it's telling me what proportion of the entries are in each class. So I'm just using these boundaries and this relative frequency to chart this out. The second class boundary begins at 114.5 and then ends at 170.5, and the height here is given by the relative frequency, and I've calculated the relative frequency here out to be 0.27, and that's what I'm charting here. So with the relative frequency histogram, it's basically the same process as a frequency histogram. The only difference is that the column we are choosing is not to represent the frequencies, but to represent the relative frequencies, right? So from this straight away, you can get some more interesting information. For instance, if I look at the third class, it tells me that between 170.5 and 226.5, about 20% of GPS navigators are priced between 170.5 and $226.5, right? How am I getting that? I'm looking at the height of this relative frequency bar, which is 0.20, which I can read also as 20%, and that gives me that information. So with the relative frequency, we are more concerned with how is it distributed? Are a lot of GPSs very cheap? In what price ranges is the distribution of these GPS devices? Right? So again, so a histogram is always going to be a bar graph, right? Which is to say it'll have all these bars, and then the height of the bar represents the column that we're charting against. If you're going to do a frequency histogram, then the height of the bar represents the frequency of that class. If it's a relative frequency histogram, the height of the bar represents a relative frequency or the proportion of the data entries which belong in that class. Okay. All right. The last thing that we might want to chart is to look at the cumulative frequency graph. And the graph of a cumulative frequency is also called a OVAC, right? So we might want to graph how the cumulative frequency itself is changing as we move from one class to the next, right? So one important thing to know about how we graph the OGI, so cumulative frequency distributions, is that we use the upper class boundary as the relevant data value on the x-axis. Because if you remember, the cumulative frequency is telling me how much of the data have I seen at the end of each class. So that's why we are going to use the upper class boundaries to label it. And this tells us how is the data, what does the distribution of the data look like, right? So here we have our usual data, the data set that we are already using. So we have these class boundaries that we have constructed. So by the time I've hit 114.5, which is the class upper class boundary of the first class, the cumulative frequency is 5. I've seen 5 of the data entry. By the time I hit 170.5, I've seen 13 of these data sets, and that's what I have here. So at 58.5, that's the lower limit of the first class. I've not seen any data entries. By the time I finish the first class, I would have seen 5 entries. By the time I've seen this, I've finished seeing the end of the second class, which is at 170.5, I would have seen 15 entries, 226.5, which is this upper class boundary. I would have seen 19 entries, and that's what this graph is telling me, right? So you can see that it tells me what the evolution of that distribution is, right? It's telling me as I move across the price point. So if you think about what's happening here, as I move across from low to high across the across the price point, how is the price of those GPS devices distributed along the price axis, right? So we can see that about 25 GPSs are between 114.5 and and 338 and between 114.5 uh, and sorry. So if I look at this, 114.5 and 338.5, you can see that about 25 of those GPS devices are located in this range. So most of those GPS devices are in this range. The other thing to note here is the slope of this graph, right? The part where the slope is the steepest, the slope is basically telling me how sharp the rise is, right? The slope of this line. So if I look at this, this is a very sharp increase. This is a relatively less sharp increase. This is not as sharp, and then it's getting flatter and flatter and flatter, right? So the sharpest increase or the greatest increase occurs when I move from 114.5 and 117.5, telling me that this is like a crucially important pair of classes. That's where a lot of these GPS devices are located, or there's something happening as the price changes from 114.5 to about 170 point, in that range between 114.5 and 170.5. Okay, so that is a, a early foray into descriptive statistics, right? So with this descriptive statistics, keep in mind as to why we are doing this, right? We have a raw data set which has just been collected, hasn't been organized in any meaningful way. We just have the raw data set. Now, in order to make sense of this raw data set, we want to impose a certain amount of structure on it, and that's the reason why we would construct a frequency distribution. With a frequency distribution, the point is to take the raw data set, sort them into different classes, and get a count for each of those classes. Then we talked about relative frequency. With relative frequency, we want to get an understanding of what proportion of the data set belongs in each of these classes. Then we talked about cumulative frequency, which tells me how is this distribution evolving as I move across these different classes. Okay. And then we could construct different graphs, different visual representations. Instead of having that big table, we can construct different visual representations of that. So we talked about how to construct a frequency histogram, how to construct a frequency polygon, how to construct a relative frequency histogram, and an OGI, which is basically the graph of the cumulative frequency. Okay. So that basically covers everything in section 2.1. Again, if there's any questions at any point during this discussion, you can always leave them in the comments below the video. I keep monitoring the comment section. So if there's anything that comes up, then you can always leave a comment there and I'll reply to you as quickly as I can. Otherwise, again, office hours are a safe bet for you to get some of these questions answered. Okay. Hope this is clear so far. Okay. All right. So let's move ahead and talk about a few more graphs and displays. These are a little bit, other graphs and displays that you might see uh, in statistics. When you're reading a statistics paper or you're reading through a statistical analysis, you might see these other representations as well, these visual representations. So we'll talk about what we call stem and leaf plots, right? So, sorry. Yeah, we'll talk about stem and leaf plots. We'll talk about dot plots. We'll talk about pie charts. We'll talk about Pareto charts. And then we'll talk about how to use scatter plots and how to do time series charts, right? So a few more of these graphs, and that's where we'll end the session for this week. So now you have a basic introduction into descriptive statistics. All right, so let's see each of these in turn. So a stem and leaf plot, as the name suggests, consists of two parts, what we call the stem and what we call the leaf. Okay. So for instance, if I have a bunch of numbers here, we use the last digit as the leaf, right? Each number is separated into a stem and a leaf, right? So for instance, if my data is 21, 21, 25, 25, 26, this is my data set. So in order for me to put this in a stem and leaf plot, the 2 here becomes my stem and the 6 here is the leaf on that stem, right? So here I write down the stem, which is 2, and then I draw a vertical line here, and then I list all the leaves which are with it. So now 21 is on the stem 2, and the leaf numbering is 1. 25 again belongs on this, 25 again is here, 26 is here, 27 is here, 28 is here, and then 30 is on a different stem, right? So if this is the way I'm representing it. So this is a stem, so 3 here, and then 0 is the leaf number. 36, 36, 45, and now we have a stem and leaf plot. Okay, so it's not very fashionable to use the stem and leaf plot as much, but you might encounter it every now and then. People still use it quite uh, some people still use it quite often, and you might see it in more or less older statistical analysis where this used to be quite a fashionable way of making these charts, right? Because it's like a nice representation. So for instance, let's look at a data set here, right? The following are the numbers of text messages sent last month. Display the data in a stem and leaf plot. Okay. Before I get into this, the one thing I need to talk about very crucially is this key. However you make your stem and leaf plot, you need to specify a key to the stem and leaf plot for me to understand how I should read this, right? So you should tell me if if you look at an entry like 15 and 15/5, then you should read this as 155 because it could mean anything, right? I could make this as 15/5, read it as 15.5. I could make any number of different representations of it. So the key here is important. You need to tell me how to read the stem and leaf plot. But otherwise, everything else is straightforward, right? The generally follow strategy is that to use the rightmost digit as the leaf, right? So in this case, I'm going to use the rightmost digit as the leaf. So for instance, uh, for the number 155, the stem is going to be 15, the leaf is going to be 5. So now I put the stem number here 15 and the leaf number is 155, right? So, and I go through the 159, I will do 15/9. So it will be on stem 15 and the leaf numbering is 9, and that's where I get that. Then 144, it will be on stem 14 and the leaf number is 4. So this is 144 and this is how I represent it. And now I have an entire stem and leaf plot. Okay. This is what we call an unordered stem and leaf plot because the entries are showing up in the order that they appear in the data set, right? There's no particular order to it. Sometimes you might just order it into ascending or descending orders as well. Because now 144 is the first one, then 140 is here, this 142 here, and like you might want that in a particular order, and say you want it in ascending order, you can just rearrange these numbers in ascending order. So 140 comes first, 142, 144, 145, 145, 147, 148. You can rearrange all of this, right? So two key elements of this is, first is to always write a key. When you look at a stem and leaf plot, the key tells me how to read this plot that you made. Otherwise, I could interpret it in any number of different ways, and the key is, for pardon the pun, is the key to the entire graph. Okay. Now, there is a difference between an unordered and an ordered stem and leaf plot, and the difference is basically whether you just put down these leaves in the order that they appear in the data set, or whether you want to just get it more organized and organize it into uh, like a coherent kind of ascending or descending numbering, so it's easier to read, right? Because if I have this unordered stem and leaf plot and you say, okay, how many 112s are in the data set? I have to be like, okay, that's 112 there. That's one. Then keep looking. And there's three. That's one way to do this. But the other way is to say how many 112s are there? Oh, there's three. Because the ordering just makes it easier to read and convey information. So uh, that's one plot that you need to be familiar with, what we call the stem and leaf plot. Okay. Another graph that you might encounter is what we call a dot plot. And dot plot is usually employed, uh, uh, not anymore. No one uses a dot plot anymore for the most part, unless it's a small data set, right? The data set is sufficiently small, it's really, really useful, right? To look at the dot plot. And the dot plot, as the name suggests, just plots down a number line between the min and the max values in the data set. And every time you find an entry, you put a dot. So if an entry is repeated, you put multiple dots. So 25 in this data set appears twice. So there's two dots here, 26 appears once, and so on and so forth, right? So for instance, if I look at our text messaging data set, I would get a dot plot like this. Okay? So dot plot essentially, so there is a 78 here. There is, there is 309s, right? Yeah, 309s in the data set, and there is 1, 2, 3, 4, 525 in the data set, and so on and so forth. Okay. So what is nice about a dot plot, right? What is nice feature of a dot plot is that it helps us identify outliers very quickly, right? If I look at this, I can see that there is a big cluster of the data here, which is cool, right? This is where it's cluster. Then I recognize it's getting sparser and sparser and sparser as I go further. But there are some kind of unusual values, right? Look at this here. This is very far from the rest of the, these are a little far from the middle, but they're still close enough to other data points to not be considered outliers. But look at this value, like 78. It's a very unusual value, right? Straight away you can see that it gives us a nice visual interpretation, or like a visualization of where the outliers in the data set are. And outliers are interesting for many reasons. One is that, why is this 78? Who is this person with only 78, and what does that say about this? So that outliers are interesting to study. Or is it like a typo? Was it supposed to be 178 and instead it's a 70? These outliers are always interesting numbers inside the data set, and you have to somehow deal with these outliers in general. Well, maybe it's just a genuine value, but it's just an interesting value then. Then it's an interesting value to study, because outliers give us more rich information than, okay, everything is in this range, which is great, which is cool. But another thing that you can see from this dot chart is like that 126 is the entry with the highest frequency, and there's a lot of clustering. So you can see where the data is clustered. You can see which entry appears with very high frequencies, which entry or number of entries appear with very high frequencies. Also, it's like a very useful visual way of identifying outliers in the data set and using that as a starting point for further investigations into the data set. Okay. All right. So that's the second plot that I want to talk about in this section, is about a dot plot. Okay. The third chart that we want to talk about is a pie chart. right? Especially when we're dealing with qualitative data sets, right? Where one of the columns is just a label. How do we graph these things, right? Okay. So with the pie chart, the idea is very straightforward. So you start with a circle or a pie, and then you divide up the circle or pie into different sections or a sector, right? The technical term for this is a sector. So you're going to divide up this pie into different sectors where each sector represents one particular category, right? So there's multiple different categories and each sector represents one particular category. Now the question becomes, what should be the size of each of these sectors? We just don't want to divide up the pie into, equal size categories. That's a pie chart, but it doesn't convey as much information. It doesn't tell me if one category is more important than the other or what is happening there. So I might want to use uh, a little bit more nuance here. And the nuance here is going to, we'll see what it is, but suppose this is the story I have, right? So this is a kind of a qualitative data set. Remember when we talked about qualitative versus quantitative data sets in the first session, we talked about qualitative data as a kind of data which is giving us information. Data is anything that conveys some information, but it's not numerical. So here we have a distribution, we have a description, a table, which tells me all these different categories of the data. So there is all these types of degrees that are awarded. There's actual real world data as to number of thousands of degrees, right? So this reads as 728,000, right? This is 1.52 million, and then 604,000. And first professional is some kind of licensing, and there's about 60,000 doctoral degrees which are handed out every single year, okay, in 2007. Okay, so suppose I want a chart to represent this data, okay. Now I know that a lot of bachelor's degrees are awarded, not a lot of doctoral degrees are awarded. So I know I want to do a pie chart, but I don't want like all of the categories to be the same size. And I want to know what proportion of the pie should belong to each of these categories. And the crucial insight here into making a pie chart is to understand that uh, uh, first to know what is the proportion of each category in the total of the data set. So if I add up all the frequencies together, they sum to 3007. So if I add these 1, 2, 3, 4, 5 numbers together, you can verify this for yourself. That's the total number of degrees which are awarded, right? 3007. Of the 3,007,000, so this 3 million degrees which are awarded, there are 728,000 are associates. So because everything is thousands, I'm just using 728 over 3,007. So 728 over 3,007, so about 24% of the data set of all degrees are associates degrees. 51% of all degrees are bachelor's degrees. 20% are master's degrees. 3% are first professional degrees, and 2% of all degrees that are awarded are PhD degrees, okay, or doctoral degrees. Okay, now given that I know the relative frequency of each of these categories, now this gives me an indication of how to divide up my circle or my pie, right? So the one thing to know is that the angle that a sector makes at the center of a circle is what we call the central angle, is 360 degrees, right? The sum of that angle is 360 degrees. So for so of that 360 degrees that is available as a total central angle in the circle, we want 24% of it to belong to associates, right? So about 86 degrees of that 360 degrees of central angle which is available should be taken by associates degrees. 51% of those 360 degrees, so 360 degrees times 51, right? 360 degrees times 51 is 184 degrees. So 184 degrees of the available area of that sweep of that sector should belong to bachelor's degrees. 20% of that 360 degrees central angle is 72 degrees should belong to masters, and so on and so forth. So if I add all of these numbers up, they should always sum to 360 degrees. Okay. Now, given that is the case, now I can begin graphing these things. How do I graph these things? So I start from the center, I draw a line, a radius, I say, okay, bachelor's degrees, starting from here, I need to sweep an angle of 184 degrees. That's roughly 180 degrees is a straight line, slightly more than a straight line. So this here represents the sector which belongs to bachelor's degrees. So 51% of this pie is bachelor's degrees, or 184 degrees of the central angle, it belongs to bachelor's degrees. Okay, so I close that off. So I label that as bachelor's 51%. Now starting from here, I sweep a further angle of 72 degrees to get to the end of masters, right? From here, this central angle, the proportion of the central angle that belongs to masters is 72 degrees. So I sweep this central angle and then I keep going that, right? So again, from here, another 11 degrees that belongs to first professional, another 7 degrees of that central angle belongs to doctoral, and the remaining 86 degrees belongs to associates. Okay. So the crucial thing is to recognize that the central angle here is the sum of the central angle here is 360 degrees, and I need to make sure that I distribute that central angle among these different categories based on their relative significance. Because bachelor's is the single largest category and accounts for 51% of all degrees that are awarded, a little over half that pie is given over to bachelor's degrees, and so on. And so that's how we find how large each of these sectors needs to be. Okay. All right. So this is how we construct a pie chart. So with a pie chart, just remember that we are taking care of relative frequency, and the size of each sector depends on the angle that that sector will sweep, or what proportion of the central angle is occupied by that sector. And to figure that out, we multiply the relative frequency of each category by 360 degrees, and that tells me the central angle which is given over to that particular category of data. Okay. All right. Pareto chart essentially is kind of a histogram. It is a histogram. You can use either frequencies or relative frequencies to make it, but you don't need these categories to be, they don't need to be right next to each other, because these are categories, these are labels. It's qualitative data set, right? Because the labels are qualitative, they're not numbers like we had with class boundaries, but they're qualitative. The other key feature of a Pareto chart is that the highest frequency category appears first, then the second highest frequency category, the third, the fourth, and so on and so forth. Okay. So, for instance, suppose you're given this data set. It's not don't know the underlying data set, but this is the information that you've given. You want to understand what loss in the retail industry looks like. Again, it's a real world data set, and the retail industry has lost about $36.5 billion in inventory shrinkage, and they managed to figure out what was the causes of inventory shrinkage, right? And they're like, okay, $5.4 billion was due to administrative error, 15.9 billion was to employee theft, shoplifting was accounted for $12.7 billion worth of loss, and vendor fraud accounted for about $1.4 billion of this loss. Okay. And suppose we want a Pareto chart, you want to present this data, and you might want to use a Pareto chart, because first you have these categories. First of all, you have qualitative data in one of these things that you're trying to graph. And the other thing is that you might want to present in such a way that the most important category, the one which deserves the most attention, is presented first, right? You could just present it in the same order as it does, but this Pareto chart is about ordering these categories based on their importance, right? So if I think about it here, employee theft should go first because it accounts for most of it, 15.9 billion. So first category is employee theft, and on the y-axis, the height represents how important it is, so $15.9 billion. Then shoplifting is the second biggest category, the category with the second highest frequency. So that's 12.7, that goes second. Administrative error is third, which is 5.4, which goes third in the Pareto chart. Vendor fraud, about 1.4. And then, this doesn't account for the total of the 36.5. So unknown is the remaining, whatever is not. Okay. So a Pareto chart, as it suggests, it tells us which category has a higher relative importance and what you should focus on. So you don't want to go through these solving these problems in the order that they appear in this table, you might want to tackle the most important problem first. And so maybe employee theft needs to be addressed as in a significant fashion first, then shoplifting, then consider cutting back on administrative errors, and then maybe tackle vendor fraud. Yeah. All right. So the last pairs of graphs that we might want to look at, some of the more important versions of this, is what we call graphing paired data sets, right? Where for the same, as each entry in one data set corresponds to one entry in the second data set. So that's what it means to be paired data sets. So we usually use what we call a scatter plot in order to show this. And here's an example. This is the first known instance of where a scatter plot was used in order to figure out some key features of this data set, right? So this is Ronald Fisher's data on irises. So he wanted to know whether, you know, if there was some kind of correspondence, some kind of a relationship between the length of a petal of a iris and then a width of the petal, right? So he wanted to know whether longer petals were wider, or if as the petal got longer, did its width shrink, right? So that was the idea. So on each petal, you have two pieces of information. You have the length of the petal, but you also have the width of the petal. That's what makes it a paired data set. That for the same unit of observation, you don't have just one characteristic that you're measuring. You have multiple different characteristics. So that's the crucial element of why we call this a paired data set, because there's this correspondence between one characteristic and the other, because they both belong to the same unit of observation, right? All right. So on the x-axis here, the petal length is charted. On the y-axis here, the petal width is charted. So how do I read each of these points? So if I pick a point like this or this one is easier to read. This is a point which has a petal length of 30 and a petal width of 12 millimeters, right? So 30 millimeters in length and 12 millimeters in width. So each of these points represents one unit of observation, and each axis is essentially charting one characteristic of that observation. On the x-axis here, we are charting the petal length. On the y-axis, for the same unit of observation, what is the petal? And straight away, you can see how useful a scatter plot is. What, even without me telling you anything, you can straight away see a pattern in this data. If I try to fit a line through all of these data points, we'll get into that towards the end of the course when we talk about regression analysis and how to fit lines through data sets like this. But straight away, you can see that there is a nice little relationship between petal length and petal width, right? So what does it suggest? So as the petal length keeps going up, the petal width also is going up, that there is a positive relationship between petal length and petal width. So as the length of the petal is, as the petal is getting longer and longer, it's also getting wider and wider. Okay, so this is very useful because in general, in economics or in statistics, we want to understand how different variables relate to each other, right? So for instance, how does interest rate and unemployment, how are they related to each other? If I increase the interest rate in the economy, does unemployment go up or go down? One way to see that is to see the level of unemployment on one axis, the interest level on the other axis, and see if there's some kind of relationship between unemployment and interest rate. If there is some kind of positive relationship or a negative relationship between those two, and now straight away you can see that, oh, if they're related in some way, then you can automatically see the wheels turning and saying, if I change, if I'm able to push, there is some policy way in which I can push on one of them, then that will influence what happens to the other. So if higher interest rates are also associated with higher unemployment, then maybe I lower the interest rate and that can bring down unemployment, right? So in general, when we are, well, at least as statisticians and economists, we are mostly concerned with trying to establish these relationships between different variables and how one affects the other. And scatter plots are by far the most common way in which we end up visualizing these things, and it becomes very useful as a form of analysis. Okay. All right. Um, Time series data, right? Sometimes, as we said, we talked about cross-sectional data. So the previous example is a example of cross-sectional data, because at one point in time, we're just measuring petal widths and petal widths of petal lengths and widths of all these different petals that we've collected. And so it's a snapshot in time. So sometimes we might have data where, we are measuring, looking at the same variable, but we are trying to see how it evolves over time. And that's what we call time series, where the axis, the x-axis is one of time, and the y-axis is whatever it is that we are measuring. So for instance, suppose we have this data from, this telecom data. So in each year, we are measuring the same two variables. So in different years, we're measuring the number of subscribers and the average bill that they're paying, right? So in 1998, there was 69.2 million telecom subscribers, mobile phone subscribers, who had an average bill of $39.43. By 1999, 86 million, and so on and so forth. So you can see what is happening. So we're looking at the same variables. We're not changing what we are looking at. We're just measuring the same variable at different points in time, right? The axis that's changing is the time axis. The variables that we're measuring themselves are fixed, right? And those values are evolving over time. And so that gives us an indication of how to graph these things. So in 1998, if I want to look at what is the evolution of cell phone subscribers over time, then I essentially look at in each year how many cell phone subscribers were there, right? And now straight away, in 1998 at 69.2, and that forms my first point. 99, 86 million. In 2000, 109.5, and it tells me what is the trend over time in cell phone subscribers, and I can see that it's increasing. It keeps increasing over time, right? So that gives me an indication of, we're looking at the same variable. We're not changing the variable we're looking at, but we're looking at that same variable as time is passing by, as time changes, and then we have what we call a time series chart. Okay. All right. So that's where I'll stop this week's session. So, this is an introduction into how we start with a raw data set, sort it into these different categories. Once we have this sorting done, how do we then begin to visualize it? How do we begin to work through it and then get a relative sense of it? So what we will do in the next session, next week, is to talk about analytical measures of these things, right? We'll talk about measures of central tendency, measures of variation, and then we'll talk about measures of position, right? So that's where we'll finish up with this descriptive statistics part, and the week after that, we'll move into probability theory. Okay, so as usual, if there's any questions, leave them in the comments. Come see me in office hours. I'm always here to help. Thanks for listening, and I will see you in the next one. Bye bye.